So, good morning, everybody. Welcome for this new IAA seminar. Today is the third seminar of the week, and we have a special guest. He will talk about resolving stellar angular diameters with asteroid occultations. Joshua Bartkoske from the University of Utah. He's a PhD student, and he will make himself the introduction. So, Joshua, thank you for coming here. And the floor is yours.
Thank you so much, Renee. I'm very excited to be here. Like Renee said, I'm from the University of Utah. I'm a PhD student, and I'll give a quick introduction. So just a quick, yes. Oh, yes, I can. Wow, I didn't notice that. Thank you for noticing that. I didn't see that. So just a quick self-introduction. My name is Joshua Bartkoske. I was born in Boston, but I quickly moved overseas when I was just a boy and grew up mostly in Almaty, Kazakhstan, where I graduated from high school in 2015, where I moved to Bozeman, Montana, and did my undergrad in professional physics at Montana State University. I graduated there in 2020, but before I did that, I spent 1 year as an exchange student at Shanghai Ocean University, studying Mandarin Chinese. So ni hao. Much better than my Spanish, unfortunately for me here. But now I'm a PhD candidate at the University of Utah, studying with Professor Dave Kita, and I've been there since 2020. A quick brief outline of what my talk is going to be today. In my title, Resolving Stellar Angular Diameters with Asteroid Occultations, the important things to know and the questions I'll answer primarily are why we measure stellar angular diameters, what are occultations, and then what is VERITAS. And these are things that are very vital for the research I'm doing. After I do that, I'll go over some broad strokes of the analysis and results that we have currently with our work, as well as what we've learned from our work, and then what we plan on be doing next. So go over that in detail. The first question that I'll answer is why measure stellar angular diameters? Well, the main reason I think, and the fundamental thing, is that measuring the sizes of stars is a very fundamental part of astronomy. It's one of the first basic parameters that we can actually measure for stars, which then are the building blocks of the rest of astronomy for understanding planets, exoplanets, and other systems. We need these sizes of stars to have benchmarks for large catalogs like Gaia. And with Gaia, we've measured now billions of stars in very, very precise astrometry, but majority of these stars are too small to be measured directly, their angular sizes. And so we need benchmarks to then have models of both stellar atmospheres and stellar evolution that allow us to then say something about the sizes of the stars that we can't directly measure. Now, one thing that's been showing up in the literature for a while is this radius inflation problem, which has been potentially due to the magnetic activity of stars, but is still a question as there's discrepancies between what has been predicted and what's been observed at low masses. And so by measuring the stellar angular diameters of stars, we can hope to resolve some of these tensions that exist between our theory and model with our observations. And another important reason for measuring stellar angular diameters is for characterizing exoplanets. When we look at exoplanet transits, we can learn something about the size of the exoplanet, but only when we have an accurate radius of the host star of that exoplanet. So we really need to measure the sizes of stars to understand all of these other parts of learning about our universe. Now, the way in which we measure stellar angular diameters there are many, many ways of doing this. This shares some of the indirect ways of measuring angular diameters. Some of these include measuring directly the radii of stars, and I'll go through each one of them briefly. The first one is using a surface brightness color relation. This is kind of using those models of stellar atmospheres and evolution, and using color and magnitude of stars to then determine an angular diameter based off of a model. We can also use eclipse-detached binary star systems, which have been observed, which accurately are able to determine both the radii and masses of the companions. But then to get an angular diameter of a star, we need to then go and use the parallax. So technically, in my work as angular diameters, it's an indirect measurement of that angular diameter. And then the last indirect method is the astroseismology method, which has been an up-and-coming field the last 15, 20 years. and which is where they analyze the oscillations of stars, and then they use the models of stellar interior, looking at those oscillations of P waves and G waves, kind of similar to what we do here on Earth with seismology, but we can use that to calculate the radius of the star. And then again, using parallax, determine an angular diameter. To directly determine angular diameters, there's other methods that are pretty well known. Two of them have interferometry, and one of them is occultations. So the first, amplitude interferometry, you may have heard of this. This is the Michelson interferometry, where you take light from multiple telescopes and at various baselines, and then you combine that and directly interfere the light. And with that, you can resolve an image of the star using that interference from different telescopes. And so it kind of lets you use a much larger bandwidth, sort of making a big telescope out of smaller telescopes that are spread out. This is primarily used in the visible or red and infrared bands, and so is not always able to image every star, but is very good at what it does. There's also intensity interferometry, and this is what was developed back in the 50s. And instead of directly interfering the light between telescopes, it actually correlates the intensities of light and can be done offline digitally. And this was largely abandoned in the 60s due to the constraints of the technology at the time. You can see a picture of the Narrabri Stellar Intensity Interferometry Observatory. And so it was quickly surpassed by the amplitude interferometry. But in recent years, this has been revived with current modern advances using ground-based gamma ray detectors like VERITAS and MAGIC, and soon to be CTA as well, where they've been able to reuse this correlation of light intensities from different telescopes to get a UV plane, and then from that fit the stellar angular diameter of the star. Another way of measuring this, which has actually been one of the ways that's been around the longest, is lunar occultations. And this was first postulated in 1902 as a way of measuring the stellar angular diameter of stars, but then was not directly confirmed until 1936 by the French astronomer Arnulf. And so I actually found his paper going through the database, and that was a really cool thing to look at the very first measurement using occultations to look at the sizes of stars. This is primarily just by looking at how long it takes for the limb of the moon to cover and or uncover the star, and also takes into account the diffraction of light around the limb of the moon. So this is all about angular diameters, but the next thing I'm going to talk about is occultations. I know there's a lot of occultation work that goes on here, so this might be a review, but for anyone online or anyone who needs a refresher, I'll quickly share. An occultation is just any time you have one celestial body that covers up another one, since occult comes from the Latin to cover. So an example of this is a solar eclipse where you have the moon covering up the sun. This is kind of the simplest one to understand how an occultation works. But you also have lunar occultations, which I mentioned before. So remove the sun and add any other star, and now you have a lunar occultation. And these are really actually great at measuring not just stellar diameters, but also resolving geometric binaries because of its fine resolution. Another thing that you can do with lunar occultations, which is really cool, is you can measure the features on the surface of the moon by seeing the dips and rises in the valleys. Another type of occultation, if you get rid of the moon and you include an asteroid, so now you're having an asteroid pass in front of a star, is you see an asteroid occultation. I do want to note that this slowdown is not real. Asteroids don't magically just slow down as they pass in front of stars. That's my Photoshop skills at work. But this is data that's been resampled from our telescope showing how as an asteroid passes in front of a star, its intensity drops out as well. And this is very helpful for determining the sizes and shapes of asteroids, which is a lot of the work that goes on here, not just for asteroids, but also transit-tuning objects and any other object in our solar system. And so it's a very, very nice way of getting those measurements. The last question that I'll answer here, I'll answer more questions if you have them, but the main one that's for the purpose of my talk is to answer, what is VERITAS? VERITAS is the Very Energetic Radiation Imaging Telescope Array System. Quite a mouthful, but essentially what it is it's a ground-based gamma ray detector located in southern Arizona that is primarily designed to observe the extensive air showers produced by gamma rays in the atmosphere. These are very large telescopes. To give a quick sense of scale, you can see me standing there kind of very faintly wearing a mask during COVID times with this huge 12-meter diameter telescope with over 200 mirror facets that collects the light and then sends it to a camera with almost 500 pixels. Now, the way that VERITAS works as a ground-based gamma ray observatory is that it is imaging Cherenkov light. Cherenkov light is this light that gets produced when you have the relaxation of charged molecules in the atmosphere, when you have a gamma ray or a cosmic ray start a particle cascade, and then as these particles that are charged move faster than the speed of light in air, they cause this relaxation effect. And so you kind of see something that's like a sonic boom, but instead of it being sound, it's seen as light. So you have this relaxation. So you see this nice cone of blue light, and that cone hits the ground, and you see an image on your camera of what that cone looks like at each section on the ground. And then with multiple telescopes, you're able to resolve the direction and the energy of that gamma ray or cosmic ray that was produced in the atmosphere. And this is important because we need to distinguish between gamma rays and cosmic rays. Since cosmic rays make up the majority of the background and of these Cherenkov events we see, we make cuts on our data to look for just the gamma rays. And so we need very precise calculations for that in simulations. What that means, though, and what you might be asking is, okay, it's a ground-based gamma ray detector. Why do we use this for occultations? Well, the reason is that we're not directly imaging gamma rays. We couldn't do that from the ground. We're directly imaging Cherenkov light. And Cherenkov light is fast, it's blue, and it's very faint. And so what this means is that VERITAS needs to have very fast time sampling and very exceptional quality at measuring its timing. So this is good for observing the fringes on occultations. We also need to have PMTs that are optimized for bluer light. And so this means that we're able to see optically, which means we can look at many, many more targets than if you're doing this in other wavelengths. We're also really good at collecting light. And so we have large apertures, and we also have multiple telescopes. And what this allows us to do is to reduce the amount of noise that we're having either from scintillation or from telescope instrumental effects that might just show up in one telescope. We can eliminate those by looking at multiple telescopes and having these large apertures, which means that even though VERITAS wasn't designed for this initially, it actually makes a very good detector for asteroid occultations with diffraction. Now, to give just a quick refresher, again, for anyone who just needs a reminder of diffraction, the diffraction that we're looking at here is, there's two types, Fresnel and Fraunhofer, but the main one that we are looking at is Fresnel diffraction, because what we're looking at is near field diffraction. So when you have a wave that hits a point or goes through a slit, you see a new set of interference fringes that show up. And in Fresnel, this shows up in near field where you're close to the object that is diffracting the light. And in our case, looking at an asteroid, it is much, much closer than any kind of star, which is very far away from us. And so we look at this Fresnel regime. This was seen with VERITAS. We looked at a couple of asteroids that occulted stars in 2018 and got published in a 2019 paper where we were able to then measure directly the angular diameters of two stars. And so the first star up top in A and B plots from the paper is TYC 5517-227-1, which was measured to have an angular diameter of about 0.125 milliarcseconds, or roughly that's about the size of, say, a basketball on the moon as imaged from Earth. So very, very small. And this directly showed it to be a K3 giant star with a spectra that was taken. The second star in the lower two plots, C and D, TYC 278-748-1, was directly measured to have an angular diameter of 0.094 milliarcseconds, and this was seen to be a sun-like star. The really exciting thing about this technique was that this was, at the time of publication, the smallest star ever observed, ever measured at the time of publication. Since that point, there's been one other star with asteroid occultations that's been observed to have a slightly smaller angular diameter. So still today, it's one of the best measurements that we have. To put this into consideration with all of the other ways of measuring stellar angular diameters, you can see on this plot, all of the green triangles are the amplitude interferometry, the circles are occultations, and the blue triangles are intensity interferometry. This y-axis is the angular size. So as you go down, you're getting the smaller stars, and then you have the distance to the stars that are observed. And this, as you're going farther to the right, you're getting further away. So the 2 points that you see down there, the two black stars, were the two stars observed with VERITAS. And if you notice, this is really pushing things down into a new regime. The two other points there that are red from occultations were occultations of stars One of them was an occultation by Jupiter, and another one was an occultation by Juno. And so this distance to occulting objects is very important. And the further away we are, the lower, the smaller stars we're able to resolve. So this has been able to push this whole field of measuring angular diameters of stars down into the sub-milliarcsecond regime, which is really exciting for future work. To kind of go into the details of how VERITAS observes, this might get a little technical, but please stay with me. We have a whole camera here of photomultiplier tubes that have little cones on top to avoid losing any light between the pixels. And in the central pixel, we hook up the current monitor to this enhanced current monitor that's off the shelf that can sample up to 4,800 hertz. And this data then gets sent to a Windows laptop with WinDAC software and then records that data. So as we're observing both gamma ray data, and then we have this additional data that we take that goes to a laptop. That then gets sent to an archive and then gets downloaded to local machines where we analyze the data. Now, in order to observe occultations, we need to make predictions. And so if you're familiar with that, predictions play a large part. Currently, what we use software that's designed for the amateur community for doing predictions, like the Occult V4 and Occult Watcher programs. And we use this currently for how we do our predictions. When we do our predictions, we update our orbits monthly from the 3 databases listed here, Asteroid, the Minor Planet Center, and ASTIS-2. And in specific cases where we're really interested in a target, we use that JPL Horizons database to get more accurate orbital parameters. Now, when we make our observations, this is what our data looks like. So there's a couple features here that I'll point out and then get into the analysis. The first thing to note is that we have these peaks, which I should say are not peaks. These are actually dips of pixel suppression. We're in negative volts here because we're using photomultiplier tubes, which record electron counts. So everything is in negative volts here. But these are dips where basically we suppress the pixel, and this is supposed to help with our timing information for relative timing between all 4 of the telescopes. And then we have our occultation, which if I zoom in on that, you can see this occultation, which again in the negative volts looks like a rise instead of a dip in the light curve. You can see very nicely, it shows the ingress and egress as well as some little bits of fringes on the edges of that. Not every occultation, though, is as good as that. We have a lot of our occultations that end up in misses for various reasons, and this is a good example of what we miss. Sometimes, in the example of this green line for T3, we get saturation because the pixel gain has been set incorrectly, and so an observer just did not actually set it correctly at the time. If you notice, there's also no pixel suppression that takes place during the time of the run, and this is an issue when that happens because it's harder for us to get relative timing. We need to find meteorites in the data. This one does not. And also just, we didn't really see anything. There's this like faint brightening in 3 of the telescopes that didn't get saturated around 50 seconds after the start of the run, but not anything significant with fringes that we can look at. So now that I've answered my questions, I'm going to move on to more talking about the analysis and the results and what we've learned. But before I do that, I do want to see if there's any questions at this point about any of the things that I've talked about. Yeah.
No, when you have this signal, I forgot the name. What is the timing accuracy in your measurement in the light curve? Is within 1 second?
Yeah, within 1 second. So
and if you don't have it, is
the pixel suppression. Without the pixel suppression, we have to find an external way of measuring the relative timing, because the way we start the timing in all of these is we have to go individually, each telescope say go, 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 go. And so this timing from the start is actually, it's 0 here, but it's slightly offset, which is why you see the occultation is slightly offset in time. Yeah. Any other questions?
Okay. I have a question about this, about the pixel suppression.
Yeah.
So do you tell the telescope when to perform the pixel suppression for the time, or so how do you make sure that the occultation does not fall when the pixel is suppressed? That's a
good question. So we take data for 5 to 7 minutes, and we tell our observers to start that 3 minutes before the prediction says that an occultation is going to occur. So the occultation happens in the center, and then we do the pixel suppression at the beginning and then sometimes at the end. but
Okay.
traditionally we just only ask for the beginning. Sometimes they do a second pixel suppression. Yeah. Yeah. All right. If no further questions, I'll continue with the next part. So moving to the next part, we start with this data that we collect, but the question is, how do we go from the data to a fit and actually get an angular diameter of the star? This is what we're trying to measure and what we really want. So I'm going to quickly go through that over the next 10 minutes. So the first thing we do is we select the data. We get rid of everything else after we've gotten that timing information. So we know the relative timing, so we can align this. We collect where the occultation is. And then the next step is we flip the data. And we flip it so that we see everything in positive volts. So these occultations look like they traditionally would in other places where you see that dip in the light curve. Once we have flipped the data, we then zoom in and we select just the little bit of time around the ingress and the egress of the data. And here you can clearly see the nice diffraction effect on either side of this occultation. After we do that, we do need to select the ingress specifically and then flip it as well in the x coordinates because of the fact that we're using a Fresnel integral, which is an odd function. So if we didn't do that, it would be negative in the way that we fit the data. And so we just align everything so that it looks like an ingress or an egress, sorry. So like I mentioned, we use a Fresnel integral, which is this equation here, depends on the distance to the occulting body, L, as well as the lambda, the wavelength of the light that we're observing with. There's a normalization factor, and then everything is in units of distance from the edge of the geometric shadow in meters. Using this equation for the Fresnel integral, this gets incorporated into a longer overall equation, which is taken from a paper, A. Richichi, 1989, where you can see that the intensity of light seen at a moment of time is given by the Fresnel diffraction, the brightness profile of the star, as well as the area of the telescope, the wavelength response, which requires a stellar spectrum. So we need that for the purposes of analyzing the data, as well as a time response of the instrument, which depends on any factors in there, and then the background. So to give a quick sort of overview, sometimes equations are much more difficult to understand. If you look at the blue curve, this is a monochromatic Fresnel integral, and then that gets summed up and then normalized over every wavelength that we have a dependence on. And that's the polychromatic yellow curve that you see visible. And then once you have that, you convolve it with the angular diameter of the star within the brightness profile, and that gives you the green profile. And then taking into account the time response function, this is the filtered / impulse, the purple curve, you get the final profile of what the model is that we fit to the data. Now, one of the things that I want to note with this is the most important equation for us in measuring the angular diameter is this brightness profile of the star. And it depends on the angular radius of the star. It does assume a circular profile, but it can have a limb darkening coefficient. And for the purposes of our model, looking at just a uniform disk, we set that to 0. So we just have this simple equation, which is just an equation of saying, here's a circle, here's how big that circle is as we go from one side of the circle to the other. And then we fit the angular radius of the star. In order to do that, we need accurate parameters for the asteroid. So we go to JPL Horizons, we query the database, and then we get both the distance to the asteroid as well as the velocity of the asteroid at the moment in time of our occultation to be able to use that as parameters for the rest of the analysis. We also get a spectrum of the star, either from Gaia or from the Whipple Observatory, which we can request. We also have atmospheric profiles because of the sensitivity of VERITAS. We need that, as well as the PMT quantum efficiency and the mirror reflectivity, which all go into this overall transmission profile that you can see here for all 4 telescopes. It's very similar between the telescopes, although there's slight variations at different places. And then after all of that, we do an initial fit to our data using a least squared reduced chi-squared method. And this initial fit is primarily to just get the right time of occultation. So this 0 point on the graph, the time from the start of the occultation is what we call it. And so this allows us to then precisely determine at what point we're going to start seeing these fringes. After we get that precise moment in time, we then refit the data, giving the angular diameter as well as the angle of incidence of the star as a free parameter, and then we fit it. And once we have the best fit, we run a posterior MC Markov chain Monte Carlo to get the posterior distribution so that we can see the uncertainties in our data. And here you can see the data for one of the stars, the occultation that I've been showing you. This is the T1 egress. And so you can see we have a measurement of about 0.1 milliarcseconds with an uncertainty of plus or minus 0.01 in our measurement of the angular diameter. Right now, with our results, we're actually currently on our way to publishing. We have at least 3 stellar angular diameters that we're going to be contributing to the overall catalog. We have 8 detections total, but some of them are still a little bit too noisy for us to say something strong about. Every single star that we're measuring has never been directly measured by any other technique that measures stellar angular diameters. So this is new parameter space for this field for measuring these stellar angular diameters. Our depth of seeing occultations right now, this is something that we've learned, is that we can actually see down to magnitude 13.3 in the B band, which isn't super faint, but is fainter than all of the other techniques currently. Our uncertainties, though, are currently at about the 10% level, so we need to reduce that somehow. And this primarily comes from the fact that we have this large bandwidth, and so it causes problems when we try and fit to the data. And the other exciting thing in our data is that we have 3 potential low mass stars in our data, which these are the stars that have the most interest for people with stellar angular diameters. Measuring these stellar evolutionary models and seeing how well they can fit the data. These are going to be important, even at the 10% level. So some of the things that we learned, well, we've learned that we can push our sensitivity down in previous iteration. In the previous paper, we only were able to measure down to magnitude 11. And this is showing us that we can push our sensitivity down a little bit further at the current way we do our occultations. Our uncertainties are still large, is though another thing we've still learned. And so we need to try and fix that with the bandwidth and potentially use a filter in order to reduce that uncertainty and get better constraints on angular diameters. Another thing that we've learned, and this is, I think, anyone with occultations learns, is that for a successful detection, we've needed on order about 20 times more predictions than we have actual successful detections. And this is primarily because of weather, which takes out about a quarter of our predictions, as well as the moonlight, because VERITAS can't observe under moonlight due to the sensitivity of the photomultiplier tubes. And so that knocks out about 50 of those, or 50% of those occultations a year. And then we're left with about 25 that we can directly observe. Another thing that we've learned over the last few years is that our absolute timing is really tricky. We'd really like to be able to contribute more to the field of measuring sizes and shapes of asteroids. But right now, the thing that's really difficult with that is you need really good absolute timing in order to have other observers join you and also give that data to other people so that they can learn more about stellar sizes or angular size, sizes of asteroids. Another thing, though, that's been interesting and curious to us that we've learned about is that we've seen a difference between the ingress and egress values for an angular diameter. And this has been seen at a greater than 2 sigma. So it's something that seems significant to us. And we've been trying to identify where this might come from. One of the reasons that we've explored, or 2 reasons that we've explored, it could be from our RC circuitry within the enhanced current monitor, or it could be the shape of the asteroid. So to show you the first one, the time delay, we recently, I guess in the last year, we saw that this time delay causes an impact on our model. And so that has been something we've looked at. But this is showing you the difference between showing the impulse in one direction versus showing the impulse in the other direction to simulate an egress versus an ingress, and then showing them compared to the convolved radius of the star. And as you might notice, you can see that it does change the overall model. But one of the things we notice in this is that the difference between the reverse impulse and the impulse itself does not show a big difference. And so we did not think that this would contribute so significantly to our ingress-egress discrepancy. Instead, one of the thoughts that we had was this might be due to the shape of the asteroid. So this is a model where I've taken the shadow of an asteroid from the DAMIT database and then incorporated it into code that was used in the Joel Castro-Chacon paper in 2019 for the TAUS-2 collaboration. And I've used this to model what we would expect for an asteroid shadow as we look at the diffraction pattern in various orientations. So to look across the middle, you see that this shows an ingress and egress here that have very, very similar profiles. There's a slight difference. You can see a little bit of a difference there already. But as you move away from the center of this asteroid and you start to get to different curvatures, you start to see a much larger difference between this ingress and egress values. And this was actually kind of a eureka moment when I first did this and saw this difference, because I matched it up to our data and it matched almost perfectly. And it was this kind of, wow, this is probably the best explanation for what we see. And so what we think now is that we see this difference of ingress and egress primarily due to the curvature of the asteroid at these individual points that we're observing the occultation. So the next steps that we're going to do with this data that I've been presenting is do a secondary analysis on every one of the stellar angular diameters that we've currently measured within our collaboration. And then from that, once we have this angular diameters, which will get uploaded to a catalog of angular diameters that are directly measured. And then we'll also be using Gaia parallaxes to be able to determine the radius of the star. And then from that, also compare it with models for what we expect from surface brightness color relations to determine just how well these models are comparing to the observed angular diameters that we've measured. These will get published later on this year in a paper, and then we'll go into my doctoral dissertation that I hope to be graduating in a year and a half. So that is the goal. Some of the things that I'd like to do, whether or not I'll have bandwidth myself to do this in the next year and a half, I don't know, but the goal would be to improve our absolute timing with the enhanced current monitor so that we can have some way of directly timing everything and contributing to the wider field of occultations. We also want to introduce a filter to that central pixel to see if there's a possible way to reduce that bandwidth and get really, really good uncertainties on our angular diameters. Also identifying how significant this ingress-egress discrepancy is due to the asteroid shape, which is even something talking today has been really useful to understand more of how much we can say about the asteroid shape with that data. And then searching for good occultations to collaborate with IOTA members to be able to incorporate them into what we're doing and hopefully contribute to the wider community. And then if we ever got the chance to, I'm crossing my fingers, hopefully get a really good occultation of a transit-tuning object and see that. And from previous occultations, there's things that we could find out, like the signature of an atmosphere, especially with our high time resolution, or potentially finding satellites or rings and contribute to the science going on here and elsewhere with the Lucky Star project. So as a summary of just everything I've talked about today, stellar angular diameters are a really fundamental part of astronomy. And so measuring them is a really important way to understand the rest of astronomy and what we do. We do this by direct measurements in various techniques like asteroid occultations, which is actually the way right now to measure the dimmest and faintest stars that we can possibly see directly with this technique. We also use gamma ray observatories like VERITAS that will observe these asteroid occultations and be able to determine the direct size of these stars based off the diffraction of light. And by fitting using both the least squares and MC approach, we can achieve decent uncertainty right now on our stellar angular diameters, even with a large bandwidth. One of the things that we learned was simulating the occultation revealed that this ingress-egress discrepancy is most likely due to the shape of the asteroid, which was an exciting discovery. And then with the secondary analysis, these results are ready for publication and will be a part of my thesis. Thank you so much. Thank you for your attention. Really appreciate getting to share this with all of you. Thank you.
Thank you very much, Joshua. The talk is open for questions. Okay. Yes, yeah.
So I'm not an expert in any of this, but how do you decide which occultations you try to observe with VERITAS? Is it just, you know, the moon isn't in the way, and
Yeah,
how do you decide which ones to prioritize?
that's a good question. So primarily, we try and observe any occultation that is above 25 degrees, usually above the horizon, that is in a star that's brighter than magnitude 13.5. And then we make sure that the moon is not up at the same time. And we say it's got a 10% probability of its uncertainty in the orbit being within 1 sigma of where we are located, because we can't move around to go and find occultations that are close by. We're just located in one spot. So we use all those parameters, and then I'm the only person working on this in our collaboration. So I'm kind of the one that there is some like personal decision of saying, oh, this one is kind of on the edge of what we might be able to see. I don't know if it's worth it when there's another occultation the same night that has a much higher probability. And then we make decisions based off of that.
Yeah, you mentioned you have like 2 or 3 low mass stars. I was curious of how low in solar masses.
How low in solar masses?
Yeah, what is low mass? Is below 1 solar mass?
I don't know that off the top of my head.
Oh, okay.
Yeah.
And the other is related. I mean, these are the first measurements on that mass regime of diameters.
I don't think they're the first measurements in that mass regime. If in the plot that I showed, there's masses of stars that are below like 1 solar radii that are lower. I don't know if necessarily they're lower solar masses, but they're closer to us, and there are some in that regime already that have been measured. Yeah. Yeah.
Yes. I'm just curious, how much of the time in VERITAS can you allocate to observing stellar occultations? Although they are a bit rare because you have a lot of conditions, but every time you have like, oh, this is a very bright star, no moon, all the conditions are good. Can you always observe, or sometimes it's dedicated to cameras?
So yeah, that's a good question. Every time that we have a good occultation, or anytime I say there's a good occultation that's worth observing, it is priority 1.
Okay.
Above everything else, unless there's some sort of flaring gamma ray source at that moment, or a gravitational wave event that we get an alert for, and then we move, and that takes priority over everything. So, but as long as there's no like alert that shows up, we get the priority. So because these only take 5 minutes of time at a time, it's something that really they are like, okay, you're going to observe maybe for 2 hours in a 1,000-hour season. That's not a lot of time that we're losing on targets.
How many gamma detectors are in the world? So
like this
that could observe this kind of stuff. So can you make the predictions for your own and for the other detectors, and send the invitation to, hey, you will have an occultation in your telescope in 2 days or something like this?
That there are other telescopes. So Magic, if you know Magic, that's one of them. HESS is another one that's like this in Namibia. And then there's the CTA, the Shrankov Telescope Array, that has 1 telescope right now in La Palma in the same location as Magic. And then we'll be building in Chile as well over the next few years. And so the one thing, like those predictions I could definitely do, and it'd be very easy to just, even with the same prediction data, just sort of select a different site and see what we would see at that site, and then send that information to them, or even just show them how to do it. Like the Occult Watcher software, these are amateur astronomer software, so it's very intuitive in learning how to run them. The one potential issue, because I don't know how those detectors are run, is the way that we set it up is we have that enhanced current monitor that's attached to the central pixel, and you need that enhanced current monitor. Otherwise, you're never going to see stars fainter than magnitude 6 or 7. So it's one of those questions of if they have that, it is an off-the-shelf component. So if there's a way that they could even do it quickly, they'd be able to contribute. But otherwise, they wouldn't be able to see the same.
You learn how to do it with your telescopes. You can teach the other one.
We could definitely teach them to do it.
Okay.
Yeah.
Questions?
Well, I have another question.
Yeah.
You said that you found very 2 sigma differences between the ingress and egress on some occultations. But were you correcting that because of the shape of the asteroid, and by doing that you can reach 10% error in the angular diameters? Or how can you get like so low if the difference in ingress and egress are so big? I don't know.
Oh, I see what you mean. Oh,
because you do them like separately and you get 2 diameters or
so that is actually so that's a good question. That's not something I've thought about. So our uncertainties might be larger than just 10% for the stars that we have that discrepancy. In the paper, there's a paper in 2021, I think it was, or 2022, that was the next known asteroid occultation measuring the angular diameter of stars. And in their measurement, they saw this discrepancy, and they said if it's due to the shape of the asteroid, that it would cause the angular diameter to appear different on one of them, but you could use one of the values, the larger value, as like kind of an upper limit and
Ah,
say,
okay, okay.
this is the upper limit of the star's angular diameter, and then the smaller one would be just underneath that.
Okay.
Yeah.
Thanks.
No questions? Okay, see none. Thank you very much, Joshua. Very nice talk.
Yeah.
And hope you have a good stay today here. Huh?
Thank you.
Hey, thank you.
Yes.